All right, so today we're going to be solving this question. I have a configuration of some sort of window, and I'm given the total area A of the window, and I want to minimize the perimeter of the window. So the window configuration is a rectangle adjoined with a half circle, and this line here is not part of the perimeter. Okay, so first let's do some geometry to solve for the perimeter and the area. Okay, so first of all, this is by assumption is a semicircle with radius times the width over 2 here. Okay, so the area of this semicircle is going to be pi r squared times 1/2, so 1/2 pi, and the radius, which is w over 2, squared, that's the area of this piece, and then the area of the rectangle is h times w, okay? So that's the area, in terms of the height and the width. And then the perimeter, p, well, let's see, so let's label all the sides here. So this is another h, and then the formula for the circumference of the circle, see if I can remember that, should be 2 pi r, right? This is going to be half the circumference, so it's pi times r. So we're going to have the half circumference, which is pi, times r, which is w over 2. And then plus, we have 2 h's and a w, so 2h w. Okay? So now that I have these formula, okay, I know that a is a fixed number, so I'm given a by, let's say, a contractor. Might be like 20 square meters for a huge window, okay? And I want to minimize p, okay? So the minimization of p is basically enforcing that the derivative of p should be 0 if p was a one variable function. In this case, we have two variables, w and h. However, this condition on the area relates w and h, so they're actually not independent. Okay, so this perimeter function is secretly just a function of, let's say, w. And so what I need to do is get rid of this h here and write it in terms of w, okay? So let's solve for h in terms of w. Okay, so h here, so let's take this first equation and let's unpack it. So hw is equal to 1/2 pi w over 2 squared minus a. That is completely wrong. Got the sign wrong. Minus 1/2 pi w over 2 squared plus a, which means that h is equal to 1 over w times this kind of gross expression. Okay, so let's do some algebraic simplification. So w over 2 squared, this is w squared over 4. Okay, and then I have a minus pi over 2 coming from the negative 1/2 pi. Okay, and then I have plus a. And then I can kind of distribute this over. So the 1 over w distributed into this summation here. When I multiply it into the first term, it's going to cancel the w squared and just give me a w. So I get negative pi over 2 times w over 4. And then when I multiply it into the a, I'm just going to get a over w. Okay, so this is the first step, is we basically solved for h in terms of w. And that allows us to plug this h back into our perimeter function and then realize the perimeter function as a function of one variable w. Okay? So let's now write p w. Okay, so it's pi times w over 2 plus 2h, and h is this gross expression here. Negative pi over 2 times w over 4 plus a over w. And then plus one more w. Okay, so to make our lives easier, let's do some algebraic simplifications. And we're going to group terms in w and 1 over w, okay? So first of all, this 2 I'm going to distribute through this expression. So pi w over 2. Okay. This 2 cancels with this 2 here, so minus pi w over 4 plus 2 a over w. Okay. So now I just have a bunch of terms involving just linear powers, like linear terms of w. So this one is a pi over 2w. Here's a minus pi over 4w, and here's a w. I'm going to group all those together. Pi over 2 minus pi over 4 plus 1. W plus 2a. Okay, so notice that I'm kind of just manipulating multiplication here. So whenever you have multiplication of fractions, you can kind of move the numbers around however you want. So this expression here is just pi times 1/2 times w. So I pulled out the pi and I pulled out the 1/2, and that gives me pi halves. Similarly, this expression here is negative pi times 1/4 times w. W over 4 is 1/4 times w. So I can just pull out negative pi over 4ths, and then I'm left with w. And this guy is just multiplied w by 1, so that's where this 1 comes from. Okay? Oh, and by the way, pi over 2 minus pi over 4, that's just pi over 4. So, after some algebraic cleanup, we have solved for our perimeter function. And now I want to minimize this perimeter function. So I want to set the derivative to equal 0. It's a function of one variable. So in calculus, if I have a function of one variable, then I know that a critical point of that function, either a maximum or minimum, is going to occur with slope 0. So that what that tells me is that I need to take the derivative of this guy and set it equal to 0. Okay, so let's take the derivative of u of w. Okay. So derivative of a constant times w is just that constant. So this is pi over 4 plus 1. The derivative of 1 over w. So remember that the derivative of 1 over w I can write as w to the power of negative 1. So this is the derivative of w negative 1. And now I just apply the power rule. So I bring down the power and then I subtract 1 from the power. So it's going to be negative 1 times w negative 1 minus 1, which is negative w to the negative 2. And then w to the negative 2 is 1 over w squared. Okay? So this is negative 1 over w squared. Okay? So when I take the derivative of 2a over w, the 2a is just a constant. Remember, area is a constant here. It's a number we've assumed is constant. So I'm going to end up with 2a over w squared, like negative. Okay? So the derivative of 1 over w is the negative 1 over w squared, and then the 2a just carries over as a constant. Okay, so this is my derivative, and now I just need to set it equal to 0. Okay? All right, so this tells me that 2a over w squared is equal to pi over 1. And I multiply over the w squared here, so 2a equal to pi over 4 plus 1 w squared. Let's divide out this number. So 2a over pi 4 plus 1 equal to w squared. And then I can take the square root. Okay, so w, taking the square root of this expression, I get this plus or minus, but we want a physical width, so we're going to take the plus sign here. Okay, this is my expression for w. Looks a little bit gross. But once I have w, I know h, because remember, we solve for h in terms of w. And just let's recall that. I'm afraid I erased the h function. So remember, the area was hw plus 1/2 pi w over 2 squared. And so this told us that h is equal to 1 over w times a minus 1/2 pi w squared. So now I can just plug in my value for W and solve for H. Okay? So that finishes off the problem. Now there's one thing that I kind of swept under the rug, which was that we just found a critical point and basically assumed that we were done. We didn't actually check that this was a minimum. It could have been a maximum. Okay? So to check that this point, we know that it's either a local minima or local maxima. Okay? And because it's the only critical point, it's actually a global minima or global maxima. Okay? And so if we look at, there's two ways you can solve this problem. The first one is if you look at the original perimeter function. Okay, so I keep erasing things unfortunately, but the original perimeter function was I of 4 plus 1 W plus 2A over W. I believe that's what we had for our original perimeter. And so if I look at this function, when W is really small, okay, this is blowing up because I have 2A over a really, really small number. So when W is really, really small, if I draw the graph here, W, when W gets close to 0, this term blows up. So the function kind of looks something like this. Okay, so it's impossible for me to have a maximum because actually this function is blowing up to infinity for W small. So what that tells me is that if I get a critical point, it has to be a minimum because there is no maximum of this function. It's going off to infinity. Okay, a more rigorous way to check this would be to